Okay, welcome to the fifth class meeting of EC 202, Introduction to Probability and Random Processes. Last time, we covered up to section 1.7. Even though I didn't read every line in the handout, I strongly recommend you to read most of the lines in the handout. Okay, so this section 1.8 is the last section of this chapter 1, entitled Probability Theory. So let me review quickly the key ideas, which is a little bit or significantly different from what you knew as a high school student a few years ago, or a freshman student who just took the probability and statistics. So the first thing, so this is very important. Whenever you talk about probability, what should be the next words? Strongly correlated. So if you are an LLM made by me, if I just enter probability in the chatting window, next words are probability of an event. Got it? So we always talk about probability, not of something strange, but of an event. So we define probability actually as a function that admits a set that models an event. Got it? So P is a set function. However, this set actually models so-called event. Event of what? So actually, we need one more concept that is most important. That is what? The concept of random experiment. So you know the famous quote by Albert Einstein, God do not play with die or something. 신은 주사위에 노름을 하지 않는다. Actually, he was very wrong, right? So he was correct in the sense that if he confined his interest to experiments, not random, he was correct. But if we include random experiments, he's definitely incorrect, right? So random experiment is very important, and people want to mathematically model a random experiment. And we know now the result. What is it? What is the mathematical entity that models a random experiment? A probability space. So a probability space now used to model a random experiment that consists of three things. So I said it's a triplet, a set with a group with three: sample space, and some textbook, and even my previous lectures at event space precisely, that is not correct. This is sample space. This is a sigma algebra of subsets of the sample space. And here comes this set function, the probability measure. Got it? And each one, sample space and the sigma algebra and the probability measure, needs to also be carefully defined. And here comes the first definition of the sample space. What is it? If we just view the random experiment as a random something generator, so this is random experiment, and it has so-called an outcome. And since this is a random experiment, we have sometimes more than one possible outcomes. We collect all the possible outcomes and form a set that becomes this sample space. Then what is this sigma algebra? For discrete sample space, which means that if the sample space is a countable set. So here comes countable versus uncountable concept. If S is a countable set, then what happens? We may choose the power set of the sample space for the sigma algebra of the subsets of S. Of course, we don't need that. As you've seen in the one of the homework problem, suppose you have a die rolling experiment, still you can choose something like this, consisting just of 4 events, may serve perfectly as a sigma algebra of the subsets of the sample space S equals 1 through 6 when we roll a die. Got it? However, we don't need this, right? We know for a fair die tossing rolling experiment, 2 to the S, that consists of 2 to the 6 events, that serves well. Anyway, so we've seen what would be possible sigma algebra. The problem is that when the sample space is not a discrete set, or if you want a countable set, then we have a big problem. And you do not notice what is problem. One of you approached me and provide me an example. I can't, I forgot. I took the course, but I cannot remember. But anyway, remember this, but whenever you handle uncountable set for your sample space, never say the power set serves well for the sigma algebra. We need something much smaller. And that is the power of the definition of sigma algebra. And why this is important? This sigma algebra has good algebraic 대수적 property, 성질. What is it? If you take any members from this sigma algebra, and if you apply a countably, possibly infinite, countable set operations, still you have an event, or you have a subset that is a member of the sigma algebra. So it's closed under countable set operations. That is the key. Got it? Anyway, then finally, we talk about this probability measure again. Since we already have, just a second, we already have defined this pair as the event space. What does that mean? If this is the sample space, this is a sigma algebra. So we have closedness under countable set operations. We only need 3 things. And the last one was quite interesting because we had something like this. What it is? This is what? Countable sum, right? So the third property is called the countable additivity property of a probability measure. And that plays very, very important role and is closely connected to our definition of the event space. Here, I said that this E is closed under countable set operations. And again, you have countable additivity. Got it? Anyway, so this is the key. And actually, this is it for all probability theory. That was very surprised me when I took the probability theory from math department with math and statistics majored graduate students. I got B when I was a graduate student. Anyway, so the professor said, you are done with just this probability space understanding. Every other definitions, lemmas, propositions, theorems are just stemmed from this theory. but we need details, of course. So anyway, so this is the key. And we had something more for the previous 7 sections. And the keys are what? The first thing was the conditional probability. And what was the second one? 전 사건 정리, total probability theorem. What was the third one? Bayes theorem. So understanding these 3 are very, very important. And what was the emphasis on the first one? You must now understand conditional probability as what? A new probability measure. So this is no longer some ratio. Of course, it's a ratio defined as it. But now you have, if you have chosen some event B from this sigma algebra, and it has probability positive, then you may define some new probability measure Q in this way. So Q of something is what? Probability of B in the denominator and probability of the input argument intersected with this event. Got it? So strictly, you can see that we have used here this joint probability of intersected events, and the single events are just this P, right? And you have defined, using this function P, a new function Q. And this function satisfies the 3 axioms of probability measure. What does that mean? It serves as a probability measure. Right? In this way, actually, you can generate infinitely many conditional probability measures if this E, the sigma algebra, may have infinite number of events with non-zero probability. Got it? So that's why I told you that everything you learn in probability theory stems just from the probability space concept and just the axiom of probability measure. What was the key of the second, the total probability theorem? From this one, actually, you need to have your mental model. So if you love baseball, then remember some your favorite players' batting average against left-handed pitcher or against right-handed pitcher. What is the total batting average? What is the conditional batting average? And even you can infer when he hit a home run, then you may say they're probably right-handed pitcher, something like that. How? Using these things. Using conditional probability definition, total probability theorem, combined together, you can derive Bayes theorem. Got it? And Bayes theorem, even though you already know, it has some interesting interpretation. Of course, you can just apply the same idea to the interpretation of the conditional probability. So here, this is the definition. And using the other product rule or chain rule, you may switch this way. And then what? And then there are basically 3 ways, but I really love this interpretation. So you take this factor in front of the right-hand side, and then you put the probability of event B together. And what does that mean? Probability of event A given event B is updated from the probability of event A without any conditioning. And if this correction factor is greater than 1, what happens? This new information given the event B actually enhances your belief about the event A. If that correction factor is less than 1, then what? It reduces, it increases kind of uncertainty, or sometimes I should be careful about uncertainty. But anyway, it reduces the probability after you observe event B. But be careful. When you write this way or that way, it does not mean A and B should occur in a sequential manner. We just mathematically write these two. However, in some cases, like the Monty Hall game show, sometimes definitely the first experiment, second experiment, third experiment is tried or performed in a sequential manner. In that case, you may interpret this one as a posterior probability. Sometimes, depending on which one occurs, this may be interpreted as posterior probability, something like that. Got it? Anyway, so this interpretation is so important. And if you replace this denominator using the total probability theorem, again, you have something very symmetrical here appearing in the correction factor. Anyway, so that was this one, and also applies to the Bayes theorem. And last time, in the previous section, we studied so-called the combined experiment, the notion of combined experiment. Sometimes a random experiment can be subdivided into so-called sub-experiments, sub-random experiments. Or sometimes, even though nobody says that this is the first sub-experiment, that is the second, that is the third, sometimes you should be able to define in your own way. Okay, let me define this one as the first sub-experiment, that one as second. You must be able to do that. And some of you already have read my handout, and it says something strange, strongly against your intuition. Given the Monty Hall show, our intuition says that there are 5 something uncertain. However, I claim that in order to prove which strategy, switch or not, is better, you just only need to concern about 3 random experiments, sub-experiments. And if you do not understand what I'm saying right now, probably you didn't read that part. So please read the handout. Got it? I will not ask you to read the textbook, but at least you read the handout. Got it? Anyway, so you combine random experiments to build a big experiment, or sometimes you divide a random experiment to better understand that random experiment. And I told you, when I first asked to precisely solve the Monty Hall problem, I spent a lot of time to come up with these 3 sub-experiments. I also initially thought there should be 5 random experiments defined, but it turned out only 3 required for me. Of course, you may define your own sub-experiments. Anyway, so the idea is that sub-experiments are combined. And when they are combined, sometimes they are combined independently. Sometimes they are combined dependently. However, in either case, we may define a new sample space, new probability space, of course, together, and new probability measure from these things. Of course, when the experiments are dependent, not independent, then you have to carefully justify why you define the new probability measure that way. Anyway, my request is that review the Monty Hall problem very, very carefully. Even though you do not agree with my definition of sub-experiments. Just, okay, let me accept Professor Zhou's division. And let me exactly follow what is the sample space, combined sample space, what is the combined sigma algebra, and what is the combined probability measure. And then derive your conditional probabilities to justify which strategy is better. By the way, so far in the weekly homework, you didn't see much problems to compute some numbers. From this week, you will see a lot. Got it? So even though this is an introductory course, here I have to give you a lot of important ideas. We are still engineering students who has to be able to solve problems numerically, sometimes using programming language. So you will see some problems asking use your own language, either Python, C++, or Java, or MATLAB. Write your own code and do some simulations, which includes random number generations. And you must be prepared to that, okay? Anyway, so this is the review, and we spent 20 minutes. So let's move on to the this chapter's last section. So here we have sequence of trials over random experiment. What is it? So sometimes some random experiments have sub-experiments that are in some sense identical. For example, suppose you toss a coin, a fair coin from your pocket, countably infinite times. And you record the outcomes of each ith trial as S sub I, something like that. And S sub I is either heads or tails. Then you want to compute the first trial at which you observe heads. You want to compute that probability. Or you want to compute the probability that at which trial I may observe some streak of consecutive heads 5 times, something like that. You may want to compute probability like that. Or something like, suppose I haven't yet shown any heads from my first trial to millionth trial. Given that event, what is the probability of event that I observe tails, something like that. Of course, you know that's still 1/2 if our trials or sub-experiments, even though they have identical probability space, when they are combined, we may need the assumption of independent combining. Otherwise, your combined probability measure must be defined differently. Anyway, so the first bullet, the motivation says that in the real world, we may have a sequence of trials over random experiment. Of course, we may have a sequence of trials of different random experiments. It's possible, right? First, I toss a coin. Second, I roll a die. Third, I do something else. That is possible. But in engineering problem, this type of a sequence of trials is very, very important. That's why we study this one. Got it? And if you need more motivation, please read these lines carefully. And here goes, so the classification or taxonomy of sequential trials. Sometimes we have the problem of defining what is a sequence in engineering. In mathematics, vector with finite number of indexed numbers is different from a sequence. Because sequence, usually you have a countably infinite number of indexed numbers, right? You have A1, A2, A3, A million, A trillion, and A sub some number for every integer. That is a sequence. But in engineering, sometimes, even though we say I have a sequence, but it's a vector. Or sometimes I have a sequence, but actually he has a vector, he or she has a vector of finite length, periodically extended forever. So you must be careful. Even in communications professors, I say sequence to mean real mathematical sequence with countable infinite numbers. But if you ask Professor Kyung-Chul Yang, he majored in sequence design, his sequence is not a sequence to me. He designed a vector and he extended that vector periodically sometimes. So be careful. That also applies to this definition of sequence. So sometimes, even though we say sequential trials, you just try finite times. But if I write the problem, I would not use this very vague definition. I would mean countably infinite number of random experiments, trials, and carefully numbered. Anyway, also each random experiment consisting the sequence may be discrete, continuous, and mixed, as you will see today. This is not yet covered. Sometimes, as I told you, each random experiments are combined independently, sometimes dependently. Sometimes, as I told you, exactly same experiments repeated again, sometimes not. However, our interest is what? In this section is identical, independent, and discrete, because we are going to flip coins or something. And what? This countably infinite. And you may say that as an engineering student, just a second, something's missing. Probably I put that bullet later, or I've already done in other page of chapter 1. So whenever you confront infinity or negative infinity as an engineering student, you may, not always, you may interpret that as what? For sufficiently large number. In order to talk about, hey, so what happens to this system if I put some very large number or put very large resource, something like that. In order to talk about that precisely, we use so-called limit operator, limit n tends to infinity, something like that. That mathematically means really very large something, and you may not claim billion is large enough for mathematician. But we engineers know that given some system, billion is large enough. Or 1 millisecond is almost infinity for some system. So be careful, okay? I realized that one, almost I graduated my, I got my PhD, if I confess, got it? So this lesson is very, very important, okay? Anyway, so let's see something else. Okay, so here, roadmap for section 1.8. Why do we have it? Because whenever we have this discrete sample space, especially finite number of outcomes, we have a very, very powerful tool to visualize what's going on. That is so-called tree diagram. And this tree diagram is not just for this sequential trials. Actually, it can be applied to your Montiel problem. Because as I told you, Montiel problem can be viewed as what? Combining of first two independent experiments, third dependent experiments. And you have finite number of outcomes, right? So you can also apply this to Montiel problem. And here goes the Here goes, yeah, here goes the figure. So you start the game, and Monty hides the BMW behind door 1, 2, or 3. So from the first node, you have 3 choices. So you have 3 edges. And these are outcomes of the first experiment. Right? And each branch or edge has the probabilities of these events. And then you have second experiment. And of course, you have to have 3 branches because the guest may select door 1, 2, or 3. But for simplicity, just we consider path only with S2, selection of second door. And then Monty opens. So you have, again, 3 branches, right? And this way, you have a tree, sometimes with finite levels, sometimes countably infinite levels, depending on your experiment. And why this is so important? Because after you draw this tree diagram, from this tree diagram, you can compute the total probability of some event. You can easily compute the conditional probability using Bayes' theorem. And I'm not going to cover this in detail during the class meeting. As I told you, I believe now, as the course changed from 302 to 202, my goal in this class meeting is to give you an idea and about the math, you do it, because the math is not that difficult and reasoning is not that difficult to our postdoc students. If you feel difficult, go to the ePacture and please ask, there was something wrong in your admission process, right? Anyway, so read it and really try to find out joint probabilities and conditional probabilities, right? Do it yourself. Anyway, so this is a tree diagram and very, very useful when you have finite number of outcomes. And probably some of you, I'm not sure, you were an elementary school student when AlphaGo beat Isidore, right? And at that time, that was a big news throughout the Korean peninsula, except those northern half. And we were amazed by the explanations like, okay, the Google DeepMind researchers say that we have 2 networks. One is the policy network, or the other is blah, blah, blah. And we simplify tree search using our algorithm, AI algorithm, blah, blah, blah. Actually, why they talk about tree? Because in the Go game, even though there are many possible choices, we still have a finite number of choices whenever we put a stone, right? So the difference is that each node has many, 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 many branches, but still the basic idea is not different, right? We think about a tree and we try to figure out some kind of posterior probability. What kind of probability? You want to find out probability of winning the game given your turn. And if you place your stone at some 1925, then is it a better winning probability? Then you put a stone in a different position. So it's exactly about computing the conditional probability of winning. And you may choose the location of stone at your turn, right? Your nth turn, given the previous stone places, that maximizes your winning probability. Got it? So if you want, you can build your own, I'm not going to say AlphaGo, probably Omega Go, not even Beta Go, but anyway, so formulate, write a programming C code or Python code to mimic this AlphaGo. Anyway, read it, okay? You can read it. Next, so this is the simplest one. We repeat independently, binary trial. And this is called Bernoulli. We know that it's pronounced as Bernoulli, but interestingly, many American and British professors says Bernoulli. They really hate French, but anyway, I will follow. So Bernoulli trials. And in Bernoulli trials, actually each one has what? Each one has two events. Two outcomes. Or sometimes you may have a random experiment that has more than two outcomes, but you are only interested in whether some event occurs or not. So you may reduce your interest to binary something. Got it? So here it says two events. Got it? And each event has probability P and 1 minus P. And then we want to compute probability of events. Sometimes conditional events, sometimes posterior probability. Using what? Using what we learned already. And the problem is that whenever we are concerned about finite times, the problem is easy. The trouble is like this. What is the probability that when you toss a coin, you never observe heads? And we intuitively know the probability of that event is 0 if the coin is a fair coin. But how can you prove it? And you may say that, well, 1/2 raised to the power of n when n tends to infinity. That is wrong. That is just a guess. That is not fully justified. You have to construct precise probability measure. And then you must select an event very, very precisely. And you must evaluate that event using your combined probability measure. And then you must show that is 0. And now you say, you don't know what to do. So actually, at this moment and in this course, you can't prove that. Because we didn't carefully prove that the probability measure as a set function is a continuous function. Probably some of you remember, I said that without proof, I'm going to claim that every probability measure that satisfies the 3 axioms are continuous functions. And in order to talk about that, you have to have the notion of limit over sequence of events, which means that limit of sets. And when you are a freshman taking the calculus, you studied sequence of real numbers, sequence of complex numbers. And if you have taken advanced calculus or introductory analysis, you learned about sequence of functions, right? And similarly, we may define sequence of subsets of sample space, for example. And then we may talk about even not just the limit of that sequence, we can also talk about lim sup and lim inf of the sequence, which has very, very interesting meaning. I'm not going to cover that. And I kind of claim that that is beyond the scope of this introductory course. However, I want you to remember this, what I just told you. There are some notions of limit over sequence of sets. And never claim that, well, so after 2 years or 3 years, you join one of our graduate laboratory, And professor says that, okay, we have to build our AI model and blah, blah, blah. So you know what is lim soup of a sequence of events? And says, you say, I don't know. You know, you don't know, never heard of? No. Then the professor meets me after lunchtime and asks me. Then I will say that, no, 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 no. Here is the URL of the class meeting. And on this specific day, I talked about it. I will claim that, okay? So this course would be a kind of little bit strange course. Usually in engineering school, we ask you to solve a lot of things or prove a lot of things, right? So we have two extremes, like math course, proving a lot of things, sometimes without knowing what is to be proved. And sometimes we compute something without knowing what we are computing. And kind of I want to balance these two. Got it? So it's like something like 교양 수학 수업, but it's not exactly that kind of class. Anyway, I will ask you to solve problems with numbers. Anyway, from this to the end, actually, you all know that, right? And because this material even appears in our high school textbook, except some of the details about Stirling's formula and some de Moivre-Laplace approximation. Anyway, we are going back to this topic, so I will skip that. And we are going back to this topic, so I will skip that. You may read it in advance if you are interested. And about this Stirling's formula, interestingly, not many undergraduate level textbooks even try to explain how this result is obtained. I'm not going to ask you to prove this one in the exam, but we are really interested in learning, right? So if you have interest in this approximate formula, please read the lines I put it carefully and understand why we have this one. Got it? So anyway, I believe I covered almost everything here, okay? Except the last one. So I told you we have countably infinite number of something, then we have big trouble. That's what I told you. And here, the key is something like this. So this B sub n, the event, is now defined in our consecutive coin tossing problem. The tails for all of the first n tosses. So you have this probability. Now, you may say that we observe only tails. Then probably you say that, okay, let me consider the limit of this sequence. As I told you, that is wrong, okay? We have to put limit here inside, right? We know that this event, strange limit of an event, is what? The event that you never observe has, right? We know that. So actually we have to compute this event. Why this is true? Because whenever you talk about probability, you have to compute the probability of the event, which means that you evaluate the event using this set function. And then actually you need to take this limit out of this function, which requires you this function to be continuous. Got it? Anyway, so this is 0. Details I will not ask in this undergraduate course. And you also have other, this is really brain teasing problems involving countably infinite number of coin tossing or something, and even the graduate level something. Don't read it, okay? Don't read it. You will be really hating this course, okay? Anyway, so there are interesting notions, interesting theorem. I would say theorem, but it's named lemma. And we have the Borel-Cantali lemma. And it was one of the most difficult lemma when I took the graduate level probability course in the math department. Anyway, so we are done with our chapter 1. And the summary is actually almost done by my review part. And only I will talk about the last part. So remember, tree diagram, very useful when you have finite number of outcomes. Bernoulli trials means that usually you have IID. And even if you have more than 2 outcomes, you are only interested in 2 events, mutually exclusive and actually partition of the sample space. And whenever you compute some probability of events, you may need combination or factorial permutation. You know those things. The problem is that when the numbers are very big, factorial permutation and combinations, you involve very large number factorial. You need approximation. That's why we need Stirling's formula. Anyway, that's all for the chapter 1. And now we are going to move to chapter 2. And as I already told you before we start recording, please update your handout to the F version. So I have been continuously updating this one and decided not to do that. So if you really want to view my not yet complete version of next chapters, just send me an email. Okay, I really want to read it before you finalize. Then I will send you individually. Okay. Anyway, here goes chapter 2, and chapter 2 has the title Random Variable. So as I told you today, everything what we are going to learn from chapter 2 stems from chapter 1. Then what is new, right? There is something new. That's why we have assigned a new chapter. And here goes the idea. Now let me skip and show you this one first. So in signals and systems, what did you learn? Anybody? Here is your hint. What did you learn, or what are you going to learn if you are taking this course in signals and systems? The left side Venn diagram is the key to understand what is happening in signals and systems. So this set, this universe or this universal set includes all possible systems. So you may say that the set of all systems. And among all systems, first we defined a subset of linear systems. What is the definition of a linear system? I'm not going to repeat. And then you also defined so-called time invariant system. And you have intersection, where you have linear time invariant systems, right? And then everything came out. What? The most important thing with this linear time invariant system is what? Using a mapping, linear mapping theory, you may say that the collection of all complex exponential functions with a different real number f, and t, here t means not just single number t, a function, right? These functions serve for all, this is very important, for all LTI systems. In what sense? If you apply choosing some specific f0 and put it here, LTI system, what happens? You obtain some complex number determined by F0 and the system property. And again, you have this output, right? This is the most important result. That's why so-called Fourier basis plays an important role in signal gen system. That's why you learned Fourier transforms, right? So the lesson is this one. Given just saying that, hey, we are going to learn a system theory, probably you can just finish that course within a week saying that a system is what? A mapping rule from the set of possible admissible input signals into the set of possible output signals. And system is a mapping rule. So actually, a system is also a triplet. You may say that, okay, here is the domain, here is the mapping rule, M, and here is a codomain. Done, right? You may say that system is a mapping rule. This may be a scalar, this may be a scalar, this may be a continuous time signal, this may be a discrete time signal, something like that, right? So just within a week, everything can be done. However, if we confine our interest by defining a smaller class of systems here, like linear systems or time invariant systems, what happens? Sometimes by properly defining a subset, this small number of, rather small number of systems having common property defined in terms of the words in the definition actually has very, very interesting results, right? So we do the same thing here in chapter 2. So this is our 202, signal gen systems 233. And now what? Here we consider the set of all random experiments. Let's start from that. So let's consider the set of all possible random experiments. And we know that each random experiment is modeled by a probability space. And each probability space has what? Sample space, sigma algebra, probability measure. Now let's focus on this sample space. And there are some random experiments where sample spaces are subsets of real numbers. For example, we roll a die. What happens? Of course, you may say that, okay, my die is not numbered. The face is 발주노초파남. In that case, you don't have any number. However, usually our die has number 1 up to 6. So in that random experiment, our sample space is a subset of real numbers, the real number set, right? Or you may intentionally assign or transform that outcome into a real number, as we do in our polls. Like, okay, if I smash you, and you may say that, so what is your pain? Number 1, okay. Number 2, number 3, number 4, number 5, almost dead, something like that, right? How can you assign numbers, actually? It's kind of arbitrary. Why this okay is just 1/2 of something like that, right? However, we do a lot of that kind of assignment. So definitely there are random experiments whose sample spaces are subsets of real. Now the question starts like this. What if we define this set and we want to find out some details, not just define the terms used in the definition, something like this, right? Here, linearity, time invariance, not defined in this term, right? However, after you intersect, you have something strange, very, very interesting, common to all the members for that intersected subset. Same thing you are going to see. So we define now so-called random variables vaguely vary from at the beginning, then we may say that, okay, definitely there are subsets of random experiments whose outcomes are subsets of the real line. Got it? Right? Then what happens? It's good to have numbers. We may apply our algebra, addition, subtraction, multiplication, division, some other mathematical operations. So definitely engineers really handle this kind of uncertainty a lot. In electrical circuit, voltage currents have uncertainties. In that case, you may model that random experiment as what? As random experiment generates real numbers. Got it? So random variable, the term, is used in that situation. So let me give you a figure like this. So before, I just draw a box saying random experiment and outcome, arrow and outcome, right? Now, we have this new label, random real number generated. And we have arrow. And here, something not that clear, but let's use our convention used in our high school probability theory part. So usually, here at the output, we use a capitalized letter or uppercase letter to mean the output with uncertainty. And saying that, okay, let me define in this way an event. So outcome is greater than or equal to 5. Got it? So we are familiar with actually this figure, even though we never drew already. We just knew this, right? But there is something really strange thing, because now let's compare our advanced probability theory learned in chapter 1. So in chapter 1, I drew this way, random experiment and outcome S. This may have an uncertainty, but I used the lower case. And when I talk about an event, I use the lower case and saying that S is even, something like that. And here, something strange. Should I use lowercase x here? Because we are going to use some strange notations like this. So we use capitalized X, we use lowercase x together when we talk about a random variable, which is related to a random experiment generating a real number outcome. Actually, this really confused me. When I studied that part from 수학의 정석 in around 36 years ago, I really hated 수학의 정석, especially in this probability theory part. I just could not understand, because that was strongly against my knowledge on mathematical definition of a function or something. What is this, right? Probably some of you felt the same thing. Why this strange notation is prevalent? Because in our high school math, everything is determined, the scope is determined by our Department of Education. They specifically say that, of course they didn't specifically say, but actually they exclude the notion of that probability space thing. Okay. Do not teach. Got it? That's the problem. And today, within 15 minutes, I will clarify why we had this strange notation and now what that exactly means. Okay? To do that, let me show you this block diagram. This is really the notion of a random variable. So the idea of random variable is very strange. Initially, I said that there are random experiments that generates real numbers as outcomes. Even in that case, we assume there is so-called underlying probability space. That is maybe interpreted as governing, controlling, or sometimes hidden. Got it? And these random experiments generates abstract outcome. Still, this S may be Baldunov-Chopanambo, something like that. Not a number. And here comes another block that maps this S to, see that? Here we have the sample space. And this sample space appears as the domain of this function, capitalized X. And this one maps each outcome of this underlying probability space, sample space, sorry, to a real number. And actually, this function is called a random variable. Got it? So random variable is a function, actually. So from now on, okay, if I or your future advisor or some person, advanced knowledge person, ask you, what is a random variable? Your answer should be, it's a function. What is the domain? Then you must say, its domain is the sample space of the underlying probability space. And what is the codomain? A real number. That is why this function is called a real random variable. If this changes to, for example, r to the n, r to the 2, what would be a good name? Anybody? Random vector. Got it? Depending on this outcome of this big generator, we name differently. Got it? If this outcome is real number, we call this function as real random variable. If this is a pair of real numbers, then we call this function as real length 2 random vector, something like that, or bivariate random variable, as we will see in the chapter 4, probably. Got it? So, even though this is not clear, think in this way. That is the kind of mathematical invention the mathematicians made to consistently define almost every random something from now on. So you will see this block diagram little bit modified again and again and again and again until the end of this semester's class meetings. So remember this. Got it? Name of this one, abstract outcome. Why? Because this may not be a number. And you have this one. Then what would be the output? See, here the output is S. Here the function is named as capitalized X. Then our now mathematical convention forces us to write the output as capital X of S, right? Nothing strange now. So the output of this function, if input is X, should be capital X of S. That is what we learned in our high school math, something like this, right? Suppose you have real in, real out function F, then what happens? If X goes in, output is F of X. Exactly same thing. Now, let's go back to this strange event. So first, actually, this is now you know that this is a simplified notation for high schoolers or 일반인, 립반진. Got it? We drop parenthesis S because we can't teach the idea of underlying probability space and measurable function as a random variable. We can't do that. That's why we just dropped. That's why you had something strange, uncomfortable. when you learn this type of notation when you are a high school student. So output should be written in this way, capital X of S. Now, then what is the precise expression for that? And that appears here. Got it? So this is kind of simplified notation, 표기법. Got it? In the zeros lecture note handout, I emphasize that you must distinguish the difference between definition and notation. There are many, very confusing notations in probability theory, unfortunately. The reason is that otherwise it's too cumbersome. You have to put a lot of bars and curly brackets and everything. So as far as we know what that means precisely, we just have simplified notation. The problem is that, problem of high school probability theory is that students and even teachers do not know the precise definition, but use the simplified notation. So this is actually an event, right? Because event is a set mathematically. So now see the right-hand side. Is it beautiful? So when we compute the probability of the event that output X is greater than or equal to 5, we must evaluate this one, right? Because you put this event here. And this P is what? The probability measure of the underlying probability space. Now, this one should be a subset of capital S, satisfying such that, this is read such that, now capital X of S is greater than or equal to 5. Got it? So this is the definition. That is the notation. But probably you remember even the curly brackets are not written this way. So I really hated our high school math because no textbook put even these curly brackets. They just wrote this way. And it really confused me. Capital P, usually we use F, lowercase, right? What is that? And suddenly parenthesis, argument over function, inequality, capital, and I just had to memorize almost everything. Now, that is over, okay? That period is over from now on for all of you. You should be able to understand that strange probability of event, X greater than or equal to 5, capitalized X, is actually this one. Got it? Now, here goes some details. And this is the definition. And you will really hate it because it's defined this way. Given an underlying probability space, as you see in the previous block diagram, given an underlying probability space. Well, is it given really? I don't know. But anyway, let's assume that that is given. So this is given. A real valued measurable function. What's that, right? Because we didn't define measurability of a function. But anyway, we know, we're familiar with this notation, and we should be. The problem is that when I was a middle school student, our textbook is 1982, 3, 4, if you can believe. No, 3, 4, 5. Yeah. When Latte Giant win the Korean series by Choi Dong-won pitchers, amazing 4 wins, 1 lose in 7 games. Yeah. It was really memorable game. Yeah. Anyway, so at that time, textbook had this type of notation. 함수 F colon. In Korea, we rarely use colon, right? And 화살표. How do we read it? function x from S into R, right? This really is very, very important in understanding every random something, because every definition containing random something in this course will exactly start from these same phrases, definition, given an underlying probability space. Or something is a measurable something, and then you have a little bit modified version of it, sometimes underscore, and you have the same S into a little bit different thing. Got it? So get familiar with this notation. Then what is measurability? So that question is solved this way. Let's go back to this event's probability. So what you want to compute is probability of event that your function x of s gives you number greater than or equal to 5. So you must be able to find this s that satisfies this condition. And as I told you, whenever you have something unknown, what you do is that we just replace something we don't know with the equivalent thing. So here goes some strange notation. Where it is? Yeah. Let me just show you this. So suppose we have some event like this. Then we define the so-called the inverse image of the event by using this x superscript inverse and this event here. So precisely speaking, this one must be written this way, because that event less than or equal to 5, greater than? Okay, sorry, greater than. Yeah, something like this. And the trouble is that we may not be able to find out this inverse image, some cases, or sometimes, even though we may be able to find this set as an event, this may not be an admissible input to this probability measure. But by saying that x is a measurable function, we confine our function x that has inverse image admissible to our probability measure. That's why we have this strange word measurability. But anyway, this is the key. As far as you understand every detail of this block diagram, then actually you now understand what is a random variable. And actually, by simply extending it to like 1, 2, countably many, as you did in mathematical induction, actually, you can certainly understand almost everything probabilistically defined in this course and not in this course. So remember this block diagram. Very, very important. Ready? Okay, what else? What else? So you read it up to, let me see. Yeah, 2.0 and 2.1 up to this part. Ready? So I will put the new homework, weekly homework on the PLMS. This time there will be many true-false problems, twice many, and some computation problems, and you will enjoy. Okay, that's all for today. Oh, by the way, due will be Monday. Ready?